I've been instructed to start even though there's not too many people here. Just one thing you should know from the start of the session, the order is going to be changed a little bit. I will talk very briefly on wall frame buildings, then Michele will talk on unreinforced masonry, and then on seismic assessment, and then on seismic isolation. So seismic isolation is being moved from session 8 to session 7, and then in session 8 I'll deal with seismic assessment and closure, and then Michele will talk about the L'Aquila earthquake. So this very brief section talks about dual wall frame buildings, which are of course common, where we have perhaps this situation where we have walls at two ends of the building and parallel frames between them. So we have to distribute the seismic forces and the resisting forces between these walls and these frames. And there is a distinction between that situation where the walls and the frames are parallel to the situation in the opposite direction where the walls are continuous with the frames itself. So the frames, the beams frame into the walls as you see in this direction. So we'll look a little bit at the differences between those two aspects itself. And one thing to mention from a start is that there are some potential problems associated with this. And this is a building that was very badly damaged in the Kobe earthquake. And in this case, you can see there's walls at the end, and then internally there are frames in the same parallel direction. But in the longitudinal direction, the long direction here, there are only frames. Now, what happens then under bidirectional loading of this is that in the frame direction, maximum drifts occur in the ground level, in the first floor, and as a consequence, there is very significant deformation laterally of the end of the structural wall, so that when this is subjected to overturning moment, the compression zone at the end of the wall is already deformed laterally and has a very eccentric configuration. And as a consequence, it can fail there, causing failure of the structure as a whole. You can see that it's ended up losing a whole story as a consequence. Anyway, looking at that frame again, this here, you see that we have the two different characteristics, the longitudinal direction and the transverse direction. And in the longitudinal direction, we have a wall coupled directly to these frames here. In the short direction, the transverse direction, the wall and the frame are constrained to have the same displacements, but there is no moment transfer between them. In this case, there is moment transfer. So we will start off with looking at the short direction model first, then come back to see what needs to be modified when we consider the long direction. I can just go over that. Well, the preliminary design choices, again, we have an incompatibility in terms of the yield displacements of the systems themselves. The frame will tend to have much larger yield displacements than will the wall itself, and as a consequence, the wall tends to enter into the inelastic region of response earlier than the frames do. And we have to make some sort of decision. The first decision we make is that we're not going to trust stiffness-based analysis. What we want to do is to make a rational decision where we choose how much of the total shear of the structure is carried by frame action and how much of it is carried by beam action. So you can see that the procedure that we're looking at here is rather similar to the coupled wall business, except that in this case we do it on the basis of shear, base shear, rather than on the basis of base moment, overturning moment. We could do it the other way, but it's more rational to do it this way. So the first choice is the frame shear ratio, BF, and we would say that of the total base shear, a proportion of this, multiplied by beta, is carried by the frames, and 1 minus beta times the base shear is carried by the walls itself. And generally, this value, how much of it is carried by the frames, generally that's less than 50%. So the walls will be the basic seismic resisting system, and the walls will be the basic seismic resisting system, and the frames will carry a lesser proportion of it. So the second choice then is, having made this decision, how do we distribute the vertical requirement, the vertical shear, up the building itself in terms of the frame? And so it's the vertical distribution of beam strength. And what has been suggested for this, in fact, this is based on some work previously done for force-based design by Professor Tom Paulet. His feeling, and certainly this is what we would do anyway in displacement-based design, is to say that it makes sense to design for constant frame shear at all levels. This implies that, in fact, that we have the same shear in all stories of the frame, and what it means is it's the same as just putting a point load on the top of the frame itself. So a single load, and that will mean that the frame has the same shear all the way down it. So what we're looking at now is the structural system that we're modeling is frames linked to walls by slabs which are infinitely rigid in plane but infinitely flexible out of plane itself, subjected to a lateral force vector, which we will get eventually from the displacement-based design. And we've said that this provides, at this stage, an unknown value for the base shear, but we are making the decision that whatever that value is, we're going to carry beta times V by the frame itself as a base shear, and we're going to apply that as a single load at the top, meaning that the shear is constant all the way down the frame system. And as a consequence, the wall is subjected to the difference between this lateral force vector and this one here, typically providing something where we have a lateral force here in the opposite direction to this, implying a point of contraflexure somewhere in the building height. It's possible, if the value of beta is very, very small, that this in fact will not be in the reverse direction, but that's uncommon. So if we know what this is, we can determine point of contraflexure, we can determine the relative moments in the beams and the columns, and the moment distribution and shear force distribution in the walls. And that's shown here. Again, this is just the previous slide. Here we have the total shears. Here's the total shear force is given by this slide down here. We allocate this much shear to the frame, and hence the difference between that and the total shear, which is this bit here, is what's carried by the wall itself. And that implies moment patterns, as is shown here. The total overturning moment on the structure at various different heights is shown here. This, we have a linear distribution of the moment carried by the frame, also shown here. And the difference between the total and this is the moment pattern in the wall itself. And we know at the start of the design process, if we've chosen beta, we know where this point of contraflexure is. And that's important again, because as with the coupled wall situation, that will be the location of maximum drift, which will probably govern the design. Well, the frame moments, it's straightforward to do what the analysis is. If we have constant shear down the structure itself, what we know is that the moments in the beams will be equal at all levels except the roof, where there'll be 50% of this values here. The column moments will be constant at all locations, and at each location, what we can say is the total shear carried by the columns, of course, is the sum of these three shears here. And at the joints, we can say that the moments at any one level here, which is the sum of this moment, plus this moment, plus this moment, plus this moment. So that's the four moments, the four critical moments at the different locations along the beam, is equal to this constant shear times the story height. So we have a lot of information for this right from the start. The difference that occurs when we have the frame actually framing into the wall itself, so that there's a moment resisting connection rather than something that just keeps the displacements compatible, is that we develop an extra bending moment here and here, such that the response of this beam here in terms of its moments induces an axial force in the end column, in the end wall here, and a compression force over here. And so part of the overturning moment is actually carried by this lever arm, this couple. And we can take that into account. It modifies the bending moment pattern up the building. It's shown here for the situation that we looked at first, which was just the situation where we have the wall and the frame connected together by flexible elements. Here, if we have the moment resisting values, then for a particular choice of the beta value, what we find is that the moments in the walls are actually reduced at the base and increased in the opposite sense at the top, and the point of contraflexure changes. But it's straightforward to consider this as well. Displacement profiles, this is pretty straightforward. The yield displacement profile, we can assume that this is linear curvature to the point of contraflexure and zero at higher levels. Now this is not valid at higher levels, but it makes virtually no difference to the estimate of the yield displacement. We are interested in then what this would imply for the displacement profile this symbol here is meant to be less than or equal to HC, if not equals to, so you might want to correct that in your slide there. This gives you the displacements at the various heights related to the wall yield curvature itself. And so this is just the height of the particular section itself and the height of the contraflexure point. If we're looking at a story that is above the height of contraflexure, so this should be greater than or equal to, then we have a slightly different expression for the displacement profile, the yield displacement profile. But with this, we know what the yield displacements are at the height of the frame, of the wall itself. The design displacement profile, frame member strains are not critical. Almost always that will be the case. So the wall displacement limits will govern. And of course, this could be the drift limits, but that will be the same whether you're considering the wall or the frame. If the material strains govern, then it's similar to what Michele has already presented. The design displacements are the yield displacement plus the rotation of the plastic hinge, the critical limit state rotation, which is the difference between the limit state curvature and the limit state yield curvature times the plastic hinge length, then just times the height. If the maximum drift, and we note that the maximum drift occurs at the height of contraflexure, so we can calculate also what the rotation, the drift at the point of contraflexure is straightforwardly. In the second case, if the code drift governs, it's just the same procedure as we've already talked about for simple cantilever walls. In very tall structures, it's advisable again to have some correction for drift amplification due to higher mode effects, and as we do in frames, as we talked this morning. So we design with a tall structure for a reduced value of the critical drift. With tall walls and frames, the drift may exceed the first mode values due to the higher mode response, and hence we're using this value. Elastically responding wall frames, well, we've talked in cantilever walls, in bridges, and in frames that structures, particularly in regions of moderate seismicity, may respond elastically, and again, modifications and suggestions are made here for combined wall frames, but they're essentially the same as for walls, and we need to make no further consideration of them. Equivalent viscous damping, well, we calculate separate ductilities for the walls and the frames, and particularly if they are parallel elements rather than elements that are joined together, we can calculate what the yield displacement of the frame are, and then from the displacement patterns of the walls, which are imposed essentially on the frame, we can determine the ductility demand of both the walls and the frames. We then calculate the damping values for the walls and the frames separately, and weight the damping values by the proportion of the overturning moment carried by the walls and the frames, just using the usual sort of expression here. So again, no problem in dealing with that in a rational sense, whereas in a force-based design, first you don't know what level of ductility to use because the ductility is different from the walls and the frames, and second, you don't know how to compensate for the differences in energy dissipation between the elements itself. Now, I've already mentioned this business here, so I can go straight past it. The way in which we can look at higher mode effects, there's a number of different ways of doing it, but I think I'll skip past this session and say, well, no, I can mention that one way of doing it is by the modal superposition system that we've mentioned before, particularly when we reduce the stiffness of the various elements to the appropriate value at the limit state displacement. So in other words, we would take the beam members and reduce their stiffness down to the cracked section stiffness divided by the ductility demand for the frames, and that would give us then a model where if we do a modified modal superposition, where we just reduce the values for the first mode by the ductility factor and keep the higher modes elastic, then we'll get something or other which gives us a very good estimate of the higher mode effects. So we could do it that way, or we could use some simplified capacity design rules. And in all the cases in the book of the different structural systems, we've tried to show the best, fairly simple, reasonable analytical approach to use for determining higher mode effects, and the second, to have simplified capacity design rules which are more convenient for straightforward design. And so what we have here is something which says that the column moments should be equal or greater than the overstrength moment, which is taken as 1.3 times the overstrength factor for material properties exceeding specified values, times the value that comes out of the design analysis for the structure. And this is pretty conservative. It could be argued that amplification is not needed, since a soft story mechanism would be controlled by the wall stiffness. And that's particularly the case provided that most of the seismic lateral force is taken by the walls. This could be problematic if, for some reason, you had most of the lateral forces carried by the frames, but that would be rather unusual. And the same system is applied or is suggested for the shear. Again, something or other where a higher mode factor of 1.3 is used, times the overstrength factor, times the shears from the analysis itself. Now, as far as the walls are concerned, we would just use the same overstrength factors that we got from the cantilever wall designs. Now, in the appropriate part of the book, and also in these notes that are handed out to you, we have a design example to illustrate the way in which this is carried out. It's a 12-story steel frame building here, but with reinforced concrete walls, channel walls at the ends. So these are essentially the same frames in both directions here, reinforced concrete channels here, and these beams here, which are, of course have moment resisting connections to the columns itself, have a pinned connection at the end connecting on to the flanges of the channel walls, because a moment resisting connection there is difficult to achieve adequately. So we see what the acceleration response spectrum is, what the equivalent displacement response spectrum is. I'm not going to go through it because it's a straightforward system, except for perhaps mention briefly the design choices. Based on the number of frames and the channel sizes, we decide to allocate 40% of the base shear to the frames and hence 60% to the walls itself. We calculate the wall contraflexure height in the usual fashion, and we end up first of all with our standard sort of expression for height distribution, mass times height, and various other aspects of this sort of nature to determine what the relative shears and moments are for the frames and the walls itself. And then the second table here shows the additional information in terms of yield displacement, design displacement, and the parameters that we need to determine the design characteristic displacement and the characteristic height, the effective height itself. It's straightforward, and you have all the information in your handout book, so I don't intend to go through it. We have more interesting things to look at. But I'll make a couple of comments on the design itself. The results illustrate a number of important beneficial effects of combining frames and walls in the same structural systems. Briefly, these are that the single degree of freedom design displacement is increased compared with the design displacement for a pure frame or for a pure structural wall when code drift limits govern the design. And this will normally be the case. The equivalent viscous damping is increased compared with a pure frame design, which means that the base shear is going to go down. Well, the combination of those 2 points above mean that the design base shear force is significantly reduced compared with a pure frame design. In the specific design example considered, the beam and column design moments are reduced to about 1/3 of the value that would apply to a pure frame design. And perhaps to discuss briefly the design aspects here, we have chosen, of course, to say that this is a dual wall frame system. We could have designed it as a wall system with gravity frames made out of steel, as in relation to the question that Gabriela asked this morning. But you can see that this doesn't make any sense in this case. We take into account everything that we can and get a better understanding of the response as a consequence. Well, the resulting economies are obvious and substantial, particularly when it's considered that the walls can be used as the surrounds for the essential services and hence. It's clear from these comments that dual wall frame buildings are a particularly appropriate structural form to maximize the efficiency advantages resulting from displacement-based design. And I think that is as far as I go.
For what concerns masonry structures, it has been a bit more fun than other chapters in the sense that it's a bit more creative chapter. Not because, I mean, everything is rather new, but in the case of masonry, there was very little in the literature under any respect. Masonry structures have never been a kind of structures that have been too much under the attentions of engineers. Actually, masonry structures are not at all as simple as someone believes that they are, in the sense that even if it is true that normally they are composed of shear walls, essentially, but these shear walls are always combined in such a way that it's almost impossible to try to design one single masonry wall to resist an earthquake force, knowing what the distribution would be of the earthquake forces, and I mean without considering the coupling that is coming at least from floors and possibly from lintels of all sorts that could be made of masonry, but could be made also with wood or other material. So I will try to say a few words just to discuss what would happen when you have some coupling due to the floors or to the masonry lintels, or when a wall is more complex, like in this case where you have smaller openings. Just to begin and to introduce the problem, the case of even a very simple masonry wall is not simple. And you can obtain very different results if you analyze a simple wall using a linear or a nonlinear response. For example, this is a very simple wall, as you can see, and what you obtain in terms of shear that is taken by each one of these three walls is very different when you look in terms of linear or nonlinear response. And the reason is, well, there are several reasons, but a main one is that when you go into a nonlinear response, you take into consideration the fact that when you are pushing in this direction, this wall is going to have a much higher compression force, and this wall is going to have a much lower compression force. And due to this effect, it happens that the response of this part here and of this part here, that in other structures, in other cases are similar, in the case of masonry can be quite different. And in fact, if you look to a case where you're just simply doing a pushover analysis of this sort, just pushing in this direction, you can see that the amount of shear that this part of the wall is taking is much higher than the part of shear that this wall is taking. There is one aspect which is interesting and related to this kind of response of a masonry wall. And this aspect is, what would you guess in terms of possible shear crackings in these three walls? Well, when you are pushing this direction, there is no doubt that you are going to have a crack in this way, and this way, and this way, and so on. But the point is, would you imagine that in the two outer walls, will you be going to have a crack that is pointing in this direction and this direction, or in the other direction, when you are going to excite the building with a real accelerogram, so that the force will be cycling in both directions? And when I ask this question to my students, they tend to respond that there is an equal probability of having the cracks in the two directions, but this is not the case. You go and look after an earthquake to masonry structures, and you would most likely see something like this, in the sense that it is always in the compression direction that you're opening a crack. So when you're pushing in this direction, you will be opening maybe this and this, but you will not be opening the other crack, the one that should come here, because in this wall you have a much lower shear, because this wall has a lower compression force. When you push in the other direction, you will be opening this one and this one. So in the outer wall of a combined masonry structure, it is very likely that you are going to see cracks that are pointing towards the two of the wall in the external direction. This, of course, depends on something that will be important in the presentation that I'm going to give, and that is what happens in these lintels. Now, if you look at this simple case, the point is that you could think to this wall in terms of three vertical walls connected by lintels. And as Nigel was describing earlier this morning, it is obvious that in this connection part, there will be a larger rotation capacity than in the vertical wall. So the damage will occur first here and here, most likely, unless you have a strong coupling made with concrete or with some tensile resistant material. But the other important thing is that if you look in global terms on what is the overturning capacity of this wall, you have two different mechanisms that will oppose to the horizontal force. One is due to the bending capacity of each one of these three walls. The other one is due exactly to the fact that this will go into, say, the compression at the lower compression level, and this will go to a higher compression level. So you have two combined mechanisms to resist the force. One is the variation of the axial force that multiplied by a distance give a moment, and the other one is the bending moment capacity at the base of each one of the walls. Exactly like in the case of concrete walls, the differential axial force is directly related to the capacity of the lintels to transmit bending moment and shear. If there is no capacity to transmit bending moment and shear here and here, then this complex wall will react essentially as three separated walls, and the only resisting mechanism will be the bending moment capacity at the base of the wall. Now, we have to keep in mind this, and now to try to recognize what are the mechanisms that a masonry wall and a reinforced masonry wall at first, and then a slightly reinforced masonry wall will use to resist a force. So let's go and have a look at the typical, very, very briefly, because I think you know this matter, to the typical damaged failure mode of a masonry walls. And these three typical ways, but actually two, are a flexural damage mode, which is essentially a rocking mode, a shear sliding wall, which is not so important because this happens only in very squat wall with poor mortar and so on. And the other one, which is on the opposite important, is diagonal shear cracking. And if you want to think about this possible damage mechanism in the frame of a displacement-based design, we need for each one of these to try to define what is the rotation capacity or the drift capacity, however you want to call it, what is the equivalent damping, and essentially to go back to the main frame that we have been discussing. So when you go and check what happens in the case of a flexural rocking failure in masonry, what happens is that you do something similar to what to do for the case of concrete, and you have a certain compression zone here, and normally you assume that there is no tensile capacity in the other part of the wall where you should have some traction, and you end up having a bending moment here and possibly a bending moment up here. But about this one I'll discuss a little bit later on, in such a way that you can write from equilibrium what the bending moment will be, and then of course you can take this bending moment and divide it by the height or the equivalent height and see what the corresponding shear strength will be. If you look at an equation like this, is a function of the vertical load, is a function of the height, is a function of the width of the wall, and is a function of the depth of the equivalent compression area. Now, normally, this A over L, over the depth, is not varying too much. I mean that the compression part is maybe 10%, maybe 15%, something like that, of the total width of the wall, so that you can make some simplification, some assumption on the ratio between this A and this L, and you end up having an estimate of the shear capacity with this kind of collapse mode, where it's essentially the two essential parameters are the vertical load and the aspect ratio of the wall. Actually, this is, of course, the reciprocal of the aspect ratio of the wall. But keep in mind, a function of vertical load and of the aspect ratio. Now, let's go ahead one step and let's try to guess what will be the displacement capacity of a wall of this sort. And if you want to look at this problem, you may again do some simplifying assumption and imagine that you may have a certain angle of the cracking of the, say, the separation cracking when you're pushing in this direction, and of course the opposite is happening when you're pushing in the other direction, so that you will try to guess what will be the curvature diagram in this part here, which is essentially what you could consider somehow the equivalent of a plastic hinge, and imagine that since normally you are dealing with relatively squat and rigid wall, that this is essentially what is producing the displacement of the wall. Well, if you do something like this, you will find out that this curvature diagram has one dimension, which is the width minus the compression area, actually half the minus the compression area, which is this part here. And in terms of curvature, the curvature will be once more a function of the deformation capacity in compression of the masonry divided by the depth of the compression zone, this part here. You should again think in terms of a distribution of the epsilon along the base. So you put together this and you say that the total curvature is this area here. So you just take this times this is divided by 2, and you end up with these values here. And now if you make the assumption of having, for example, a 0.4% shortening capacity of the masonry, you end up with something of this sort. And of course, you again make some assumption on the ratio between the compression part and the width, and you end up with something that could be in the range of 0.8%. So what I'm trying to say is that it is not true that a rocking wall could go to very large drift, because there are limits, and these limits are essentially a function of the capacity of shortening at the compressed 2 of the wall. So let's assume that 0.8% is a reasonable value for the rotation capacity, for the drift capacity of a wall of this sort. Now you go in the laboratory and you do some experimental test, and you see that in this case, this is the kind of cycles that you obtained. And that's the reason why you needed to do some numerical evaluation, because you are not sure at what point this will go before starting the crease. And you see that there is quite a little damping. This area is small. If you think in terms of equivalent damping, I'll show you in a minute that you will get something which is in the range of a 5% additional damping, not more than that. Now let's have a look at the other possible failure mode, a shear failure mode, something that implies some sort of diagonal cracking that may be in the mortar beds or may even cross the bricks or blocks that you have in there. Well, some commonly used expression is a function of two terms. One term is essentially depending on, again, on the vertical load multiplied by a friction coefficient. So this is because you are going to open a crack, but this crack will not be so large that will not be able to transmit some shear. And the other part, the other term, this term here, is essentially a function of the compression area multiplied by some sort of shear strength, which should be think of in terms of a cohesion or something like that. Now, if you play with numbers and you take out the vertical load and then you put the vertical load, of course, down here, and you see that you can make some simplification considering that the vertical load divided these two will be the compression strength multiplied by a factor which is again depending on the vertical capacity of the wall. You end up with something where you could guess that the shear capacity, the total shear capacity in this case, is only a function of the vertical load, and this factor that multiplies the vertical load could be in the range of the value which is given there, let's say 0.4 to 0.5, something like that. Now it's important to remember that then you have one failure mode which is a function of the vertical load and of the shear ratio, and the other failure mode which is a function only of the vertical load. This means that changing the shear ratio, essentially you are changing the damage mode from one mode to the other. So slender wall will essentially collapse in a flexural way, and the squatter wall will essentially collapse in a shear way. And of course, just putting the two things together, the two equations together, is easy to see what is the range of aspect ratio where you're not sure which one of the two collapse modes will be the one that will actually take place. But going ahead, now you go again into the laboratory, you do some experimental tests, and you end up with something of this sort. And in this case, you do not need to do any assumption, because you will immediately see that you have a strong decrease in the strength capacity of the wall, and maybe you could accept to go somewhere here when you have a decrease of maybe 20% or so in the capacity, and this corresponds to something in the range of 0.4% as a drift. Now, I'm just giving figures to clarify the ideas, but these figures of, say, 0.4% as a limiting value for a shear collapse of a reinforced masonry wall is a rather common value that you will see in the literature. In that range, most of the experiments done around the world have the limiting of the drift of a wall that goes into a shear failure. So now you compare what happens in terms of energy dissipation. I mean, these cycles are certainly fatter than the one that were taking place in flexure, and you end up with a plot of this sort. These are all experimental dots in here. So you have something in the range of 5% additional damping in a flexural mode, and it's not increasing because you do not have so much dissipation when you go into a nonlinear range. While in the case of this kind of behavior, until you are up to this value, you have a small dissipation, then the dissipation increases, and what you see is something, you have kind of a step function, which is around 5% up to a certain value of drift, and then it goes up to somehow 10% after a certain value of drift. And you can see that this drift could be maybe in the range of 0.2% or something like that. So what you can conclude, forgetting about shear sliding that I said is not so important, is that you have something of this sort, and I will come back to this later on. The implication of this is that with a wall where you have a flexural failure mode, you can go to a larger drift, but you have a smaller equivalent viscous damping ratio. So you have a correction factor of the displacement demand, which is larger than the one that you have in the case of shear, that will descend from this 15%, 5 plus 10, equivalent damping. So in a way, you have two different modes. One, you have more strength. In the other, more strength means that you have a different, you have more strength that will result from the fact that you have more correction on the displacement demand, and in the other case, you have a different period of vibration. Everything's different. Now, before going to how to use this data, let's consider briefly the case of, say, a slightly reinforced masonry structure. Slightly reinforced masonry structure is common in many areas of the world. Just to put some horizontal bars in the mortar beds, it is more difficult to have vertical reinforcement, but in some cases there are blocks where you have a hole where you can put some vertical reinforcement. For flexure, I won't say anything more because you take the same stress block that I was using earlier, and you simply add the tensile capacity of the steel. So it's something similar to what you do with concrete. But if you go on the opposite to the case of the horizontal reinforcement, then you can add the contribution of shear in a similar way to what you do with concrete again, and you see that this factor is the factor that essentially counts the number of bars that are crossing a 45-degree crack, and this is just a factor that takes into account that the bond between horizontal reinforcement in a masonry structure is not as efficient as in the concrete case, and therefore normally also the contribution of steel is much less efficient. So this factor comes from experiments. But if we want, in the case of reinforced masonry, to see what is the drift capacity, then we should try to calculate what the plastic hinge length would be. And here there is an equation which is derived from the case of concrete walls with some correction. You may remember this is essentially the same. This is the length due to the penetration of the heel penetration. This is the same part. This is different because, again, there is a different efficient in the vertical direction due to the loss of bond. And of course, you can count on this part here that in many cases is giving the main contribution because again of the low bond efficient of a masonry structure. So this factor of 3 is just because this factor is taken from the case of concrete. So you can use this, and you can derive from the plastic hinge length the yield rotation and the ultimate rotation, just substituting some value, and you will be able to calculate the drift capacity of a reinforced masonry wall, which will not come out to be so much larger than in the case of an unreinforced masonry wall. As you will see, if you do some calculation, you will find in the book some example. Now, to solve the problem and try to find a way of designing wall structures, we need a few more tools. One point is that you remember that at the beginning I was saying that you can have a bending moment at the base of each one of the walls, but you can have a bending moment of opposite sign also at the top of the wall. Well, the bending moment that you can have at the top of a wall depends essentially on the weight that you have on top of the wall. If there is no weight, you have no restriction capacity, and therefore this is a free end. It can rotate. So in a way, what I'm trying to say is that if you take something like a situation here, for example, and you have some floor here, then you have the weight coming from the floor, the weight coming from the upper part of the wall, you can have something like this because the floor is trying to rotate, and is trying to rotate putting some reaction into the wall, and also its own weight is trying to react. Well, it's not difficult to write this sort of equilibrium, and this sort of equilibrium can be written in this configuration, and you see here what happens. You have all the ingredients, the two moment here, the two shear values here, and the two weights of the floor and of the upper wall. The other thing that we need is to look at cases like this one, where you have a lintel which is coupling the two walls, or a case where you have only the floor which is coupling the two walls, and this is the easier one because you know the moment capacity. But then there is probably the most common case where you have a floor passing here and you have some lintels on top of it. Now let's look what happens if you want to try to have a measure of what is the coupling capacity of this situation. Well, if you have a floor here and you have a coupling masonry element here, an unreinforced masonry element here, what happens is that you do not have any tensile capacity here, you don't have any tensile capacity here. So this case is essentially the case that I was describing earlier for a vertical wall just rotated of 90 degrees. What happens is that you have a diagonal compression strut, and on the opposite you have the floor here that should somehow guarantee equilibrium, because here you have a horizontal component, here you have a horizontal component. So the bending moment diagram here will be something like this, where you have a value which is close to 0 at this point, and the value here which is essentially due to the distance between this point here and this point here. While on the opposite, if you take into consideration the case of a reinforced masonry coupling beam, let's say, the situation is different, because in addition to a compression capacity, you have also some tension capacity, and therefore the bending moment diagram looks like this, where you have your limiting moment here and here, and you of course end up to the point where you have the vertical shear. Now what happens is that you can calculate on one side what is the rotation that you can have here as a function of the rotation of the two walls. So imagine that the two walls are behaving in a rocking way. Then you know that you are assuming that you can go with the two walls to 0.8% rotation. And then looking at geometry, this 0.8 rotation will be essentially here. And then as a function of the depth of each one of the two walls and the length of the coupling beam, you can write down what is the rotation that you need here, which is always larger than the rotation of the wall. So if you have, say, 0.8% capacity in the two walls, you are going to have a larger demand here, and you should see whether you can cope with this or not. Well, considering all these ingredients, what we have been trying to do is to give some design tool. And these plots that you see here are very similar to the plots that Nigel was showing earlier this morning in the case of coupling of coupled walls. The difference are that the number of stories here are limited, and already to go to 5 stories is a large number. And here you have an evaluation of what the equivalent height of the structure will be as a function of the total height. So if you have 1 story, clearly it must be 1. If you have 2 stories, it goes down, and then it goes down more and more. And this is what happens in terms of the beta factor, the same factor that Nigel was using for concrete coupled walls, as a function of the total overturning moment versus the moment which is taken through the coupling beams. So this factor is giving you how much of the bending moment will have to be taken by flexure at the base of the columns, at the base of the walls, and what fraction will have could be taken as with a differential axial force. And you can see that this is variable, but you can also see that if you look at this part here, you are commonly in the range, let's say that if you are between 2 and 4, even up to 4 story, you are in the range of, say, 0.75 or something like that as equivalent height. And you can see here that you will be maybe in this range here. So you are in the range of 0.4. So what this plot is telling us is that for a masonry wall, probably you are in the range of 40% of the total bending moment taken through differential axial action, and probably 60% taken by bending moment capacity at the base of the walls. Well, at this point, all the ingredients are there. So on one side, we have to decide what level of displacement, design displacement, we want to use. And this design displacement will be a function of all the considerations that I have been doing up to now, so that you can start and say, okay, we start from this level of displacement, we have this geometry, this is the kind of mechanism that we are going to have, therefore this is the kind of drift, and you can design everything in the same way as we were doing in the other cases for the other kind of coupled walls. Considering, as usual, the situation, the effects of the floors here, if the situation is that you have just the floor, which is the simplest of the situation, you know what the bending moment will be here and here, provided that they will be controlling, and or what they will be if they will not be controlling, because the rotation capacity will be the one given by the walls and not the one given by the floors. So again, we go and check all this matter here, all this number here, and you will end up with something where you could guess what your design displacement could be. And in most cases, you will be surprised to see that you have something which is not too different from this value here, which is in the range of 0.6% of the height of the wall. So if you start from something in that range and then you go with all the steps, you will be able to see whether what is the level of force that you should, of strength that you should have in each one of your walls. There are examples in the book. There are cases where you see these cases here with different values of the load coming from the floors, the weight of the wall, the other weight coming from the floors, and with different width for different walls, and also considering the possibility of having different values of the axial forces. For reinforced masonry, you do something similar. You start from certain value of rotation, and therefore you evaluate what your design displacement could be. You calculate, you assume a value of the damping, a value of the equivalent mass, and you do exactly the same procedure. Also, for the case of reinforced masonry, you will find an example in the book, and the example is the one that is depicted here, where you have walls where you have, say, smaller openings, and cases where you have larger openings, And if you look at that example, you will see what will happen in terms of design of all this case. There are two more issues that I would like to touch before going to the isolation subject. One is the case of torsion. I have never seen a problem of torsional response in an unreinforced masonry wall treated in any way in the case of a force-based approach. In the case of displacement-based approach, the procedure is rather straightforward because, again, you do exactly what has been discussed this morning. So you calculate what the eccentricity is, you calculate what the rotation stiffness is. Multiplying these two values, you can obtain what is the level of in-plane rotation that you need to have, and you can transform it into a displacement in both directions, in the x direction and in the y direction. And of course, what will happen is that you have to subtract this displacement to the displacement capacity that you want to use. So in a case of a rotation, you are essentially reducing the design displacement because you are using part of the displacement capacity to cope with the rotational demand. The last point, which is not a trivial one, it's quite interesting, is the problem of out-of-plane response of masonry walls. And this, of course, is not just interesting for the case of a masonry structure, but it's the case of infills, for the case of parapets, for the case of chimneys, and so on. If you try to figure out in your mind what will happen for a case of out-of-plane response in a structure where the walls are also responding in their main direction, what will happen is that you will imagine to have, assume to have a seismic action in one direction. This seismic action will be taken by the walls that have the strong direction in the direction of the excitation. So this wall and the other walls will act as a filter so that at this level, the acceleration will be the acceleration at the ground floor filtered by the walls. What happens is that if you assume to have one main period of vibration, what we're going to have here will be something which will be much more, if you look in terms of acceleration spectral shape, it will be much concentrated around the period of vibration of the structure in this direction. So the excitation at this floor will be very different from the excitation at the base. Now, consider what will happen at this out-of-plane wall here. This out-of-plane wall will be excited by the excitation that will come here and that will come here. These two excitations are certainly different, but they are likely to be not so much different because the filter is the same. So you should now imagine to have the out-of-plane wall which is excited by an earthquake, but that earthquake is not a natural earthquake. It's an earthquake which is filtered by a system with one more important way of responding. So what we will do in this case, what we suggest to do, is to consider the seismic demand based on the filtering effect of the building and diaphragms, and to look at what happens in the out-of-plane direction, comparing the demand that will come from that excitation with the out-of-plane displacement capacity of the wall. So first of all, looking in terms of what the demand will be, imagine that you know the displacement spectrum coming from the earthquake, the one that you have at the base of the wall. Now, if you think in terms of this displacement spectrum up at the first, second, third floor, and so on, you have essentially a filtering effect, which is due to the combination of the two periods of vibration. I mean, of the period of vibration of the structure and the period of vibration of the out-of-plane, the period of vibration of the in-plane structure, and the period of vibration of the out-of-plane structure. So, if you look in terms of something of this sort, you have this, say, amplification factor, which has a shape of this sort. You know very well this kind of shape. So it has a larger amplification when the period of vibration of the out-of-plane structure and the period of vibration of the in-plane response will be similar and will be very low when the two, and going to 1, when the two periods of vibration will be different. So what we will do is take the displacement response spectrum at the base of the wall and filter it through something like this, depending on the ratio between the two periods of vibration. The only other thing that we have to take care of is that while when we are looking at the base of the structure, at the structure responding to an earthquake, if you have a very stiff structure, the displacement that you have is essentially 0 because you are thinking in terms of a relative displacement. In this case, we want to have the displacement at the floor. So if you have a stiff structure, that displacement will not be 0, but will be the ground displacement. So instead of using something where you go to 0 here, we suggest to use something that goes to the ground displacement. So in a way, if you have a stiff structure in the in-plane response, we're assuming that at the floor level, you have the displacement of the ground and not 0. And then you filter this with something of this sort. Now, on the side of the capacity, well, it depends, of course, on the structure you're looking at. If it's a chimney, it's a completely different thing that you have to look at. But if you're supposed to look at what happens in terms of a structure like this, what you could do is to write sorry. So they need signatures. Okay, thank you. If you look at something like this, you should write the equilibrium of this wall, writing the equilibrium in the out-of-plane position. This is something that will come out also in the second part of this lecture when I will talking about the rocking response of structure. So suppose that you have a certain displacement here, and then write down the equilibrium with the vertical force and the vertical force here, and so on. And it is clear then when you increase this displacement, you should decrease the horizontal force that you need to pull the structure out of plane. In the deformed position, you have a larger capacity, and as long as you have the structure displaced more and more and more and more, you go towards 0 at the level that corresponds to the fact that you cannot find that the structure will be blown out of plane. So if you do something like this, you will have your say displacement capacity curve, which is a curve that depends on the displacement demand and on the applied lateral force. So this is the end in the sense that what we'll suggest to do is to compute the force displacement curve of the wall, which is this curve here, then to make an assumption on the response displacement. For example, this is already the answer. For example, half of this value here, to imagine that the structure will respond somewhere here, and then to compute the corresponding effective stiffness, which means that if you assume this displacement, you have a stiffness that goes up here. And doing that, you know the period of vibration of the out-of-plane structure at that level of displacement. Now, if you have this out-of-plane period of vibration, you can use it to enter here. That period of vibration is this period here. And you know the period of vibration of the in-plane response of your structure because you have already designed the structure in plane. So you will be able to plot something of this sort, which is the amplification factor of this plot, and therefore you will multiply this by this to have an actual displacement. And this is what is written here. And then you check whether the displacement that you have assumed is correct or not. So you do something like this. You guess a displacement here. You compute a period of vibration. You compute this spectrum here. You enter here with the period of vibration, actually the ratio of the period of vibration that you have calculated, and you read the displacement here. If this displacement is the same or is close to what you have been assuming here, then it means that your structure will actually behave like that. If the two displacements are quite different, you have to iterate and to find what is the displacement that will give you the proper period of vibration of the out-of-plane response to have actually that demand coming from the in-plane action on the structure. And this is it for what concerns the masonry structure. What time am I supposed to finish? Quarter past, okay. It's not easy. Okay. This section will be possibly a little bit longer, but the other one will be shorter, possibly. Will be short, yeah. So I'll talk now about seismic isolation, which is a fascinating technique. Actually, as I was saying, actually there is no closure. This is just seismic isolation and energy dissipation. And if I should have more time, I will love to discuss about seismic isolation in the ancient time. There is some writing by Plinius about the 60s after Christ. You know that Plinius was the admiral of the Roman fleet, and he was at the anchor in front of Naples when the Vesuvius erupted in 60-something after Christ, and he died there because he was a scientist. He was the admiral of the Roman fleet, but he was also a scientist, and so he wanted to go to the land and to watch directly what was happening, and he died in the eruption of the Vesuvius, the one that destroyed Pompeii and Ercolano and so on. And it's fascinating to see that he was talking about the Templum of Diana, whatever you want to call her, in Greece, that was destroyed before he was born, Plinius, and it was constructed something in the 5th century before Christ or so. And in this book he says that this templum was constructed on layers of sand and animal's fur to reduce the effects of earthquake on that magnificent structure. Well, if you want, I give you all the Latin and so on. It's very fascinating. And someone is pretending that this was the first example of isolation of a structure, because there was this floating layer that, well, I'm not sure if this is true or not, but anyway, it's very interesting to look at these kind of things. And it's also very interesting to see that there have been a number of isolating devices that were invented in the 19th century. And in the 1908, after the Messina earthquake, where 100,000 people died, there were some isolators that are very similar to those that today are used, that were not used, but they were patented. We have the patents of those devices. And they were not used because some very famous professor of that time said, this is fantastic. If we could be able to put a house on springs like we do with a horse carriage, this will be fantastic because the earth will pass under that building like just a bump under the carriage. But unfortunately, the building are not carriages, and therefore it's better not to do it. Actually, I believe that he was right in the sense that the technology was not advanced enough. But anyway, let's try to have a look in another short fashion. This is something that I already said yesterday, talking about bridges, so I won't repeat it. These are just the purposes, and I was also discussing something related to the fact that you can have a very large number of different ways of isolating a structure, but the key issue, the basic thing, is that if you look in terms of acceleration, you can have a reduced spectrum because of an additional energy dissipation, and you have an elongation of the period of vibration, so you certainly are going to have a significant reduction in terms of applied force. But if you look in terms of displacement spectrum, even if you have a reduction in terms of displacement corresponding to the corner period because of the added dissipation, in most cases you have a very significant increase in the displacement demand. So I will try to go very briefly through all the points that we need to touch. Of course, the capacity of carrying vertical loads. gravity loads, at least for certain classes of isolation devices. The displacement capacity, the horizontal force capacity, the equivalent second stiffness, the equivalent viscous damping, the recentering capacity, the post-elastic response, and the post-ultimate response. Okay, these are all items that we should touch to be able to do some proper design of a base isolation system. I will not discuss all the tests that we have to go through and so on, because I don't have time to do that. There is something on the book, and there is much more in the literature. From the point of view of capacity design concepts, the idea is that we want, again, to avoid any nonlinear response which is not in the isolation system. We want to control the post-elastic deformed shape of the structure, in general increasing its global displacement capacity, and we want to increase the energy dissipation capacity to reduce the displacement demand. And then we want also to try to have structures where, if the intensity of the earthquake that will hit the structure is larger than the one that we have designed for, we would like to have something that does not have a step behavior, that will behave in a proper way up to a certain level, and then it will destroy. It will be a disaster. We want to have something where there is still some proportionality between action and damage. And this is not always the case in base isolated structure. I will try to discuss devices considering essentially bearing devices and devices that are only dissipating energy and do not bear any vertical structure. So if we are looking at this kind of bearing, the one that are also taking the vertical loads, the essential points are those that are given in this slide. Well, now let's consider first something that is not normally considered an isolation device. This is what has been used for years and years for bridges, just using pot bearings, just having low friction pads, PTFE on steel. This is actually a kind of an isolation device. It's similar to the one used in the Templum in Greece. It's not a control device, but in a way you have something where, if you look at a force displacement plot of something like this, the force that you are going to have here is essentially a function of the vertical force multiplied by the friction coefficient. And consider also the fact that even during a response to an earthquake, you are certainly going to have a larger force, vertical force here, and the lower vertical force here, but the total force will remain the same. So if you accept, and this is not true, but anyway, if you accept that you have a linear relation, I mean that the friction coefficient will remain the same, essentially the response will remain the total response, will not be modified. Now, if you look at something like this, what you will note is that you have a very large energy dissipation capacity here. If you think in terms of equivalent viscous damping, and you try to do an equivalent calculation using the relation area divided by 2 pi, whatever was written in these 2 days, you will find out that the equivalent damping of something like this is 64%. So it's an extremely large value, but unfortunately there is no recentering capacity, there is no control of the response, and what is possibly more important is that you will not be behaving, going along this or something like that, but it is like you may remember the famous sliding block of Newmark. So the structure will respond without any movement there for a large variation of acceleration, and then we'll go to move there only in the cycles that will exceed that value, that will activate the friction between the two of them. A more common isolation device is just a rubber bearing. A rubber bearing, you know it probably. A rubber bearing has a number of steel plates in it, and the reason I show it in a minute, the reason, well, first of all, look at the displacement that you could obtain out of something like this, but anyway, and you can have also failure, as you can see. And these are photographs taken in my laboratory. This is a very large device. But essentially, the point is, what is the vertical capacity? Well, strange enough, the vertical capacity depends on the shear modulus. And the reason why the vertical capacity depends on the shear modulus is that the rubber has a Poisson ratio of about 0.5. So there is no volume variation. And when you put a vertical load on rubber, the rubber tends to bulge to an increase of horizontal displacement, which is the same as the decrease of the volume due to the vertical load. So if you imagine that this piece of rubber cannot displace horizontally in this part here, where it is in contact with the other surfaces, and you have a deformation which is bulging like that, there you have a very large shear deformation. And therefore, it is the shear deformation that controls the vertical capacity. That's why here you have a vertical capacity which is a function of the area, a function of the shear modulus, a function of an aspect ratio. This aspect ratio depends on the diameter and on the thickness, and on this factor here, which is the deformation capacity in shear of the rubber. This shear modulus is in the range of 1 megapascal for rubber. This gamma factor is in the range of 1. So as you can see, the only real variable is this factor here. Now, this factor here is not depending on the total thickness of the wall, of the rubber bearing. It would be depending on the total thickness if you should not have the steel plates. But if you have the steel plates in here, then this height is the distance between the steel plates, because the steel plates will act as confinement. And instead of having a complete bulging, you're going to have little bulging from one to the other. So what I'm trying to say is that this is exactly the reason why they put steel plates in a rubber bearing. It's just to increase the vertical capacity and consequently to be able to have relatively tall devices without reducing their vertical capacity. Now, the other thing is that this area here is not the total area, but is the area that will remain, the base will remain covered by the upper part after you have displaced it. What I mean is that, look at this. In this case, you see this upper part here and this lower part here, the rubber has a low or almost none vertical reaction capacity. So the way of transmitting the load from here to here is to have some compression strat here. So if you go with this point beyond this point, you will lose completely equilibrium. That's why this is just the area that will remain on top of the base area when you consider the deformed shape. For this reason, you already have one maximum displacement there. And this maximum displacement is a displacement that should still allow to have the upper part, which is on top of the lower part. So in the maximum displacement normally cannot be significantly more than half of the planned dimension of the device. And from the point of view of the height, the horizontal displacement cannot be much larger than the total height, because this means a gamma factor equal to 1. Actually, the rubber could be to much more than that, but this is what is normally used to design one of these devices. If you do all this calculation, you end up that a device of this sort is normally capable of sustaining a load in the order of 10 megapascal. So it's comparable with concrete or something like that. If you do all this and you consider the fact that you have this limitation in displacement, then you can immediately calculate something of this sort, where what is written here is the standard relation that gives you a period of vibration in terms of mass and in terms of stiffness. But as I was saying, the mass, the mass is the weight, and this weight depends on the shear modulus. So you can put the things together and you end up with something of this sort, where you have the diameter over the thickness, and you end here the period of vibration, and this is the total height. So if you have, for example, a 200 millimeters device in height, and you have, again, a kind of a shape factor of this range. You end up to be somewhere here, and you will read a 3 seconds period of vibration. Okay, I'm just putting there a lot of ingredients to try then to have something on design, so I'll try to go a bit fast on this part, otherwise I'll stay till tonight just to explain how the different devices will behave. Let's forget about vertical stiffness. The response of a lead rubber bearing is different. Lead rubber bearing means that you put kind of a central part in your rubber bearing which is made of lead. Lead is a very pleasant material because it has essentially an elastic, perfectly plastic response. And it recovers completely. It is not damaged if you go to cycle into it. So what happens is that since the rubber has a shear modulus which is in the range of 130 times larger than the one of rubber, you have an initial branch which is essentially depending almost only on the lead. And you have a second branch, this one here, that essentially depends only on the rubber, because the response in this area, after you have reached yielding in the lead, the lead is essentially perfectly plastic. So this, the stiffness of this branch here is essentially the stiffness of your rubber alone. And you can work on these values again. You can see that you have a displacement capacity that gives you a certain value in terms of ductility, which is in the range of 13. If you do calculation, you'll immediately see that, because it's the rubber that gives the displacement capacity as a function of this G modulus. And you end up again with something where you can design your structure, your isolation system. But the difference now is that in the previous case, the only damping was provided by a real kind of viscous damping. And for a rubber bearing could be in the range of, say, 10 to 17, 18%, depending on the kind of rubber. But in this case, you have this very large cycle, and therefore you have large values of equivalent damping that could be in the range of maybe 30% or so. And essentially, this depends on the ratio between the total shear that you take versus the elastic shear. So in a way, it depends on this part here over this part here. Or if you want to see it in another way, the more the shear is taken by the lead, the more you're dissipating. The more the shear is taken by the rubber, the less you're dissipating, because this cycle tends to have a larger stiffness here and a smaller value here. And this is the kind of plots that you obtain. But commonly, you can be, if you stay in the range of 2, which means that you are taking approximately the same level of shear with the lead and with the rubber, you are in the range of 30%. And you also have, of course, some recentering capacity due to the rubber. The third and last isolation device, then I have to say something on dissipating devices, is what is called the friction pendulum system. I was already saying something on this, so I won't spend too much time. The point is that you have a capacity of moving along a spherical surface, and therefore you have two different equations for the period of vibration. One is the standard one, the other one is the period of vibration of a pendulum. If you equate this to this, you end up with formulas where essentially the stiffness, the equivalent stiffness of the system depends only on the weight and on the radius of curvature. So this is a very interesting device. There are several problems, but this is the kind of response that you obtain. You know, you have some value here that depends on friction. Common values for friction are in the range of, well, in the dynamic range, maybe 3-4%, something like that. They are larger in the static situation, you know, the one that you need to start movement. And then the second line here depends only on the radius of curvature and nothing else. You see that you have some nice shape of the loop, and this shape will be larger if you increase the friction, and if you decrease the second line, which means that you are making the surface flatter, When you go to a completely flat surface, you go back to the first example that I was giving. Now, the problem here is, again, that if you want to do the things in a proper way, and very few people in the world have been recognizing this, is that the crucial point is that if you want to check the upper structure, you should consider the static friction. The maximum force that your structure is experimenting is due to the instant when you start the movement. Because at that point, the friction is likely to be 2 times the friction. It could be that this is larger, but this is when you are here, you are just in a situation where maybe you are stopped, the structure is behaving with a fixed isolation system, and then you start again from maybe here, but you don't start from here, you start from somewhere above here because of the static reaction of your device. Anyway, forgetting about all these difficulties that are at another level of description, again, you can have something of this sort, where you have a friction coefficient here, you have an equivalent damping here, that will be obtained as a function of the displacement divided by the radius of curvature. So you see that if you stay in the range of 3 to 4 for a dynamic friction, you end up in something in the range of maybe 20% or so. So you are normally dissipating less energy with a device of this sort, but you have a larger displacement, you have a larger recentering capacity. A few words on dampers. I will describe only 2 kinds of dampers. One is a very simple one. It's a piece of steel. Essentially, a piece of steel is an efficient damper if you design the shape of this piece of steel in such a way that plasticity does not occur in a plastic hinge region, but plasticity occurs everywhere. So if you have something where you have a cantilever, you should have some shape which is a tapered shape in such a way that you have a lower moment here, a larger moment here. You try to have most of the steel participating in the dissipation. And of course, you could design different shape and even more complex things. But what you should look at is the strain amplitude as a function of the number of cycles. For earthquakes, you probably stay in the range of maybe certainly less than 100 cycles. So you could go to something like 4% or so strain in the steel. These are kinds of very complex steel dampers that have been used to dissipate energy in bridges. This is designed this way to keep it flat. And of course, one part will be related of these 2 parts here in a different color will be fixed to the 2 parts of the structure. And this E-shaped part are designed to dissipate the maximum possible amount of energy. And these are just bridges where these hysterectic dampers have been mounted. And these are tested in a laboratory. And this is the kind of loops that you can obtain. So you are essentially dissipating energy. And you see that if you look at the first 10 cycles or at 50 cycles, the shape does not change. This is the one that I was showing yesterday in the case of the Bolu viaduct. And this is what happens during a test in the laboratory to each one of these, say, partial moon-shaped piece of steel, where you have some of them which is elongating and some of them that become shorter, you see? And therefore, each of them will behave in such a way that it's seen in this photographs taken in an experiment. Okay, I already talked. The only one I will say something more is talking about dampers. So this is not to take any vertical capacity, it's just to correct the response of a structure, is what are called hydraulic dampers. These are very interesting devices, particularly, for example, when you're dealing with large bridges. And they are particularly interesting when you need very large displacements and maybe not so high forces to be transmitted. They are good in displacement capacity more than in transmitting forces. And if you look at the shape of this, you should recognize that this kind of devices have been used for a long time for a completely different purpose. they've been used as lock-up devices in bridges. When you were permitting to have displacement, slow displacement due to thermal movement and so on, and you wanted to have a full reaction when you are going to have some dynamic action, for example, a braking effect of a truck, or also some other kind of dynamic action. Now, what is the difference between a damper and the locker device, which are exactly the same in shape and so on? Well, the only difference is the liquid, which is inside it. And they have the same equation. The typical equation is that the force that passes through there depends on velocity. And depends on velocity through a constant and an exponent. Now, the difference is that when you want to have a lock-up device, this exponent is probably in the range of 3 or 4, so it's larger than 1. When you want to have a damper device, this exponent is probably in the range of 0.1 to 0.2. And this exponent depends only on the properties of the oil, siliconic oil or whatever, you have inside your device. Essentially, what happens is what's shown here. If that exponent is larger than 1, you have a plot of this sort, so you're going up rapidly. If it is much lower than 1, you are coming in this way, so you have something which is rapidly flat. So you look here, you take, for example, the alpha equal to 0.1, you have, remember, this is force versus velocity. It's not force versus displacement. So it's something that we're not used to use in a structure. But if you see what happens when you have a low exponent, what happens is that you have a constant force, or a almost constant force, over a large span of velocities. So during an earthquake, if you have something of this sort, you could guess that the force will be varying, but not varying so much during the response, during the earthquake. And this is very convenient, of course, because you want to control the force which is passing through there and not go beyond a certain force because you want to protect the upper structure. If you want to know what happens in terms of a force displacement response, well, a force displacement response, this, don't forget, this is real viscous damping. So what happens is this. If you have an exponent equal to 1, that is an ellipse. If the exponent is more than 1, it tends to become closer and closer to a rectangular shape. But this is not so important, but the important thing is, if I give you a structure like this and I ask you, what is the equivalent stiffness? What will you respond? What is the period of vibration? What do you respond? You do not have an equivalent stiffness. You do not know. You are going here, here, here. What happens? So that's essentially the problem. But on the other side, the good thing is that you have a large energy dissipation capacity, of course, very large and very stable. Okay, this is just the equation of this, so there is nothing much that I have to say. But the answer to the question that I was giving you a minute ago is that you will never use a damper alone. You will always have a damping system combined with something which is essentially a spring. The spring could be a concrete structure, could be a steel structure, could be anything you wish, could be a real spring, but normally what happens is that you have something like this, which is your damping device, and you have something which is like this, which is the elastic force. If you combine this and this, you just take the sum of the two, you end up with something like this, and this is something that we like much better. This is the usual plot that we're using. So it's a plot that could be thinner. When is it thinner? Well, of course, it is thinner when this response is dominating with respect to this. And it is fatter when this is dominating with respect to this. Nothing difficult. And in fact, you could look in a simplified way to this problem in this way. Just assume that your viscous damping is a rectangular shape, and then you take the spring, and what you make the difference just looking, since the displacement must be the same, you make the difference in the amount of force that you take here with respect to what you take here. So if this force is equal, you end up with something like that, and approximately you have 25% dissipation capacity. If this is 1.5 times this value of force, you have maybe 20% dissipation capacity. If you have 2 times, you have maybe 17% dissipation capacity. Okay, now we have a tool that we could use for design. And actually, okay, this is just to show you that very large devices can be used. This is one of the devices that been used in the Rion-Antirion bridge, where both Nigel and myself were involved. And this is the deck of the Rion-Antirion bridge. And this is the connection of the deck to the top of the piers. You see this, and this are hydraulic dampers. They have a capacity of 2.6 meters displacement. And this one here, this is not a damper. This is a sacrificial element that is just keeping the deck in an unmoved position in standard condition. But when the earthquake comes, it breaks off, and the bridge starts reacting, controlled by the hydraulic devices. And it happened. There was an earthquake in, I don't remember, but maybe 3 years ago in Patras, not far away. Actually, it was close to the Corinth Strait, so it was not far away from the bridge. And these were broken off, and the bridge behaved properly. This bridge is the Rion-Antirion bridge. It's between Patras, it's between the Peloponnese and the continental Greece. It's a cable-stayed bridge with span of 562 meters, and there are four main spans. It's a very nice bridge. Okay, last of the situation that, well, it's not the last actually. Well, you forgive me maybe 10 or 15 minutes more. Rocking. Rocking is certainly a kind of natural way of isolating a structure. I've already discussed rocking actually, because when I was talking about the out-of-plane response of a masonry infill, I was exactly talking about rocking. So if you want to see what happens in the simple case of a block like this was a problem that was discussed by Hausner in '56, and then Nigel wrote a paper. One was that on the damping that you can obtain due to the impact on the ground and so on. But if you write the equilibrium in the displaced position, you end up with something of this sort. Of course, you can make it more complex or less complex, whatever you wish. It depends if you have a tensile capacity here, which is this R over T here. It depends. Okay, you can simplify it or not here, but in any case, you will come out with something which is essentially of this sort. And this, for example, is given just making some simplification and coming out with a function which is a function of the width of the wall and of the tensile force that you provide over here. Now, what will happen is that you could design different structure reacting in rocking, considering that you can certainly change this reaction force here, and consider that you could change the aspect ratio of the wall. And what happens is that you can have a parallel line like this when you are changing the tensile retention here as a function of the weight. This is just to make it non-dimensional. Or you could have something like this, where you're modifying this when you are modifying the when you are modifying the tensile, we're keeping constant the tensile force, but modifying the weight this weight as a function of the weight that you have down here. But let's go and see in not more than 10 minutes the main issues related to design, which is this has been all introduction. But now 10 minutes design. Stiff buildings. Stiff buildings is very easy, very simple. What you do is that if you assume that a building is very rigid with respect to the isolation system, essentially you are only designing the isolation system. What you will do is that you take your building, which has been designed, for example, for gravity, and you know what is the shear capacity of the building here, or maybe you may increase it later on, but doesn't matter really. And you use a model which is a very simple model, which has a mass. It has an infinite stiffness here. It has a finite stiffness here, which is the stiffness of the isolation system that you do not know yet. So what are you going to do there with the isolation system? Well, this is probably the simplest of all possible structure to be designed with a displacement-based approach. Because what you do is that you have to assume a certain value of displacement, design displacement at the level of the isolation devices. You have to assume a certain level of damping to know what is the action that you have to put there. And of course, you will assume this equivalent damping, having in mind that you will use, that if you want to use a rubber bearing, you probably assume maybe 15%. If you want to use some sort of friction pendulum, you maybe use 20%. If you want to use a lead rubber bearing, maybe you use 30%. Or if you want to use a combination, which is unusual for something like this, but if you want to use a combination of, for example, some very low friction pads and some damping, you'll do your own assumption. But in this case, normally, you use either rubber bearings or lead rubber bearings or friction pendulum. Well, if you do that, you have all the ingredients, because you just assume these two values. You enter in your spectra shapes, and you have no problem. So these are the values that you may assume. So these are the value of the equivalent damping, and these are the correction factor for a standard input or for a near field input. No problem at all. Well, the problem could be that, actually, the problem could be a technological problem. Because if you have a structure like this, you may say, okay, I'd like to put 9 isolators below each one of the columns. But don't forget that if you use, for example, rubber bearings, there is a correlation between the vertical action and the horizontal stiffness of the bearings. So if you want to have a certain value of period of vibration that comes out from your spectrum, you may end up being not able to do that, because the vertical action will maybe be too low, and you have to use certain size of the isolator. So you may end up having a need of using maybe, I don't know, just 4 rubber bearing, and to use 5 pot bearings. Actually, pot bearings are more expensive than friction pendulum, so you may end up with something like that, finding that a friction pendulum isolation would be less expensive. Or you may say, well, why should I use 9 isolated devices? I could use 4. But if you use 4, then you need a slab here capable of taking the loads coming down here and putting them here. And then you need to have the lower slab here that will be able to take these loads and to put them on the ground. So there are kind of problems. Talking about L'Aquila, I will show you many isolator devices. But anyway, this is something that you may keep in mind. What happens if the buildings are flexible buildings? It's not more it is more complex, but it is straightforward from a conceptual point of view. Because what happens is that you cannot assume that this part here is infinitely rigid. Actually, this should be the standard approach, and you may design it using this approach with all sorts of buildings. So what you do is to say, well, I have the building up there, I already know the geometry. If I know the geometry, I know the yield displacement of that building. Now, I want to protect the building with my isolation system. So I want that the shear force in the building will be lower than the yield force, than the yield shear force in the building. So this means that the contribution of the building to the total displacement will be, say, 80% of the yield displacement of the building. So what I'm trying to say is that if you now want to have a design displacement there, of the total design displacement, this will be the combination of the displacement of the contribution of the building, which can be guessed at the beginning of the process, and the contribution of the isolation system. But then there is the other aspect that you have to consider. The other aspect is that now the total damping is not the damping of the isolation system. It's the combination of the two damping. And this combination is a function of the relative displacement. So if you have a very flexible structure, and that flexible structure has a large displacement with respect to the displacement of the isolation system, even if the isolation system is dissipating a lot of energy as a large equivalent damping, then if you combine the two as a function of the displacement, you find out that the global damping is relatively low because the isolation devices are contributing only to maybe 20 or 30% to the total displacement. So you may end up finding that for flexible building, it's not convenient to have an isolation system. And this is not surprising after all. Anyway, what you see here is quite straightforward because it is just the application of what we've been doing all the time today, and with the simplification that the response of the building will always be in the linear range, so that you only need to calculate the yield displacement of the building and nothing else. If you do that, then you can assume these are just the yield rotation and the yield displacement of frames and walls, the one that we've been discussing this morning. And then you calculate the equivalent height of the building, and you calculate the total equivalent damping. And now you have all the ingredients, and you do what we have been discussing all the way today. For rocking, rocking is maybe to enter in some detail will require more time than what I have now, but it's a very interesting concept because you could use rocking, for example, to design tanks, to design bridge piers, not necessarily separated, I mean using them at the foundation level and so on. But what happens is that you can have, as I was discussing earlier, if you look in terms of force versus displacement, you can have different straight lines that could even go up, not necessarily come down, because of the effect of the tensile force. So in a way, what you do in this case is that, again, you enter with a certain design displacement. Suppose that you take a drift of 2%. Now, if you use a drift of 2%, you will immediately end up with a certain required period of vibration from your design spectrum. And this means that if you have the design period of vibration, you have the stiffness, and if you have the stiffness, you have the force. So you know that you want to design for this point here. But to design for this point here, you may design a rocking wall that has a response of this sort or of this sort. So you have several options. And these options are free options, are design options. These are not part of a design process. Of course, you could also decide that you want to dissipate energy. I don't know if I have written this. Yes. You may decide that you want to dissipate energy. And the best way to dissipate energy is to use the retaining force to dissipate energy. So what happens is that you could use, for example, unbonded restraint cable on the tensile side. If you do that, you are almost for sure not dissipating energy, because if you use a 30 meters long cable and you consider the elongation of this cable, you will never go to a displacement that will imply that this cable will go into the plastic range. But you could do something different. You could use a cable and design the length that you want to have for an unbonded part of the cable, so that you are concentrating the elongation of the cable on the length that you want. Or you could do something else. You could, instead of using just a cable, you could use a cable and then to connect it through some, for example, steel dissipation device. Or you could also put at the side of the wall one of those hydraulic dampers. And have the wall that rotates and the dampers that open and close, just to dissipate energy, and of course providing a certain retaining force which is constant. So I think that this kind of of discussion are discussion of the future because you are essentially controlling the damage. You can have no damage for any level of earthquake if you design something of this sort. This is what I was trying to say. If you combine something which is due to rocking that comes down with some kind of damper, you obtain something of this sort, which is that famous flag shape that we have been discussing. And maybe we are thinking, but how do we obtain a flag shape response in terms of force displacement? Well, here is shown how you can obtain it. And of course, this could go up, but it could also be almost flat or something like that, depending on the combination on what happens in rocking, that, as you know, if you have no tensile force, will go down this way, or what happens in the damper, whatever kind of damper you're using. So you could design your rocking wall or rocking pier or whatever to have no permanent displacement because you go down here. Maybe you don't have a very large equivalent damping, but maybe you don't care too much about that, about having a very large equivalent damping. Now, about complex system, not more than 5 minutes. Okay, you know, read the book and you will see, but you could use dampers, for example, in a steel structure where you could consider to have some elongation here, which is the elastic elongation of the bracing, and then to have inside the bracing some kind of damper that will start moving before you reach the yielding in the bracing. So again, you have no damage. Or you could conceive to have, this is a bit expensive, but in principle you could put a whole damper here instead of putting there. Well, in the book there are the equations that you could use. They're quite simple and straightforward, but you obtain something like this, where you have, you calculate what the yield rotation is in terms of the deformed shape of this rectangular element, and this of course depends on the elastic deformation of the steel, if this is a steel bracing, and the procedure is quite simple and straightforward. The last thing I would like to point out is that you could very efficiently design coupled walls using couplers that are dampers. So instead of having in this part here something like the Tom Poley designed with diagonal reinforcement and so on, that will imply that you will have a very significant amount of damage in case of design earthquake, you may have something where in here you design some kind of, for example, a steel damper. You will find in the book an example where there is a design of a steel damper with a double triangular shape. And it's obviously a double triangular shape because you want to have something where in the center you are only capable of transmitting the shear, but you want to try to dissipate as much energy as possible. So what happens is that you know that you have a large rotation demand here, but in this case it's exactly what you want. You want to have a large rotation demand because you want to dissipate energy. And you could design the distance, the distance that the length of your device, because you could have some part of the concrete of the wall that comes out, and you can design the length that you want. So you could do something where you control everything, and that after the earthquake, you may have only to substitute some part, and you can design the way of substituting those parts. So it's a total control of what's happening. Of course, you could do even something more, because in this case, you are assuming to have a plastic hinge here and here, so still have some damage at the base of the walls, but you could design two rocking walls coupled by damping elements, and maybe having some small retaining capacity at the edge, given by some small cable there. And you have designed a structure that has no damage, you control the response, and so on. And this is just, you'll find in the book the way there is also a detailed example, so there is nothing complex, and therefore I stop here, only 10 minutes later than expected.
All right, we'll make a start on the last session. And in this last session, first I'm going to be talking a little bit about displacement-based seismic assessment and also looking at inelastic time history analysis, which is really part of this. And then following that, Michele will give a presentation on the L'Aquila earthquake. Good. Well, now you can all sleep as well. So let's look first at a bit of background associated with assessment of existing structures. Generally, this tends to be force-based. In other words, we determine the strength of a building itself, typically in terms of the base shear capacity, and compare this with code required strength and come up with some capacity demand ratio. New procedures include assessment of ductility capacity using simplified rules, for example, FEMA 356. Pushover analysis is widely used without an understanding of the limitations of this procedure, because of course it doesn't represent the higher modes at all. Research efforts are directed towards probabilistic assessment, with some difficulties here, as we'll subsequently discuss. Let's think of a few philosophical issues which might be relevant, and one of these is, what limit state should we be considering? Is there any need to consider serviceability or even damage control? Should we just be considering collapse prevention? What is the acceptance criteria? With new design, we have basically a pass-fail mentality, which still prevails in our design, despite the fact that we use probabilistic seismic hazard assessment. This is inappropriate for assessment. New design standards or relaxed standards, which should we be using? The rationale for a relaxed standard is of doubtful validity. In other words, what we're doing is, if we say that we strengthen the structure to 50% or some other number of the design required for a new strength, unless we know what the risk associated with that is and are prepared to accept that, we should not be doing it. Probabilistic assessment of vulnerability can be difficult, as we'll see in a minute. Talking about risk being hazard times vulnerability. To what level, once we've determined the performance of a structure as assessed, to what level of strengthening should we carry out for the structure? The same standard as for new structures or something different? Now let's look at vulnerability and some of the issues that can be a problem with this simple example. And we'll just say this is characteristic of, I don't know, it doesn't really matter what it is. It can be a single bridge pier because that's simple to understand. And we'll say that in terms of the expected material properties, of course we don't know the exact values typically, this is the expected flexural capacity here. And this point out here is the limit to ductility capacity at which we would expect a flexural failure. We also look at the shear capacity, and we say, here's the typical shear capacity which reduces with displacement ductility. And these two happen to intersect at this point here. So this is our best estimate of the ductility capacity of this bridge column, 3.1. However, if we look at uncertainties associated with the material properties, first we know that the actual overstrength flexural capacity might be very much larger than this. The material properties could be substantially higher. There might be some strain hardening, which we haven't taken into account here. So this is the capacity itself. Now we see that intersects with this shear capacity at this point here, a ductility of 1.1 or something like that. So a relatively small change in the assumptions on the flexural material properties has resulted in a change of the ductility capacity from 3.1 down to 1.1. So you can see it can be very difficult to get a realistic assessment of what the strength is. The shear strength may also be lower than our best estimate for the shear strength, which may mean that depending on what the flexural strength is, we get a failure at this displacement ductility or this displacement ductility. So there's a great deal of uncertainty associated with this in many cases. Let's look at some of the standard force-based assessment procedures. The classic capacity demand approach is based on the base shear strength. We calculate the base shear capacity and compare it with code required strength, either for a new design or a reduced value which is set as being appropriate for assessment. No assessment is typically made of the actual displacement or ductility capacity, and no capacity design check is included to determine undesirable failure modes very often. No estimate is made of the risk associated with the strength, the base shear strength divided by the code strength being less than 1. In other words, it's not common, at least yet, to determine what that risk means in terms of, say, annual probability of exceedance. A simple strength-based assessment, then, without consideration of displacement capacity or risk levels, cannot be considered a satisfactory approach and has really little value. Now, since then, we've moved along and equivalent elastic strength assessment is sometimes used, and this is a mixed strength and displacement approach. A pushover analysis is carried out to determine the force displacement response, and a displacement equivalence rule is used to determine the equivalent elastic base shear strength. So we say, here's our calculated response of the structure, and this is the maximum displacement ductility capacity. We then say that, for example, the equal displacement approximation holds, so the elastic displacement with unlimited strength would be here, and we can compare that value with the elastic response level, or if you like, this displacement value that would be for that period for the code with the capacity of the structure as calculated. Problems with this, the displacement equivalence rules tend to be rather inexact and people can't decide what we should be using. Again, capacity design effects are not considered and risk determination can be a problem. Another technique which is popular amongst researchers is incremental nonlinear time history analysis. Basically, the procedure is the structure is analyzed for response to a suite of spectrum-compatible accelerograms where the intensity is scaled to different increasing levels until the limit state that we're considering is reached. Problems with this? Well, it's a large number of analyses are required. The spectral shape should change with intensity. In other words, if you're looking at seismic risk, then we shouldn't be just scaling the same records by the same factor. We should be using in each level of analysis a different spectral set which represents the probable risk associated with that level. For example, if you're talking about a 50-year return period, this will definitely be dominated by small earthquakes close by. If you're talking about a 1,000-year return period, it's probably dominated by a large earthquake at some distance. And the shapes of these will be completely different, so you can't get anything valid by just scaling the spectral set. Again, there's the problems of uncertainty of material properties affecting capacity design approach. So in theory, you should repeat this for a wide range of variable material properties. And of course, the whole thing gets completely out of hand, except as a research tool. What we need to have is data of this form where we have relationships between the displacement capacity as calculated and the code displacement demand that we would have for that structure, have relations between that and the annual probability of exceedance as shown here, so that we could, having calculated this value, come across to the curve and find out what the risk associated with that is. And we note that normally seismological data will be available related to the peak ground acceleration demand capacity ratio, but some interpretation will be required in a displacement-based environment. And this just shows that, in fact, looking at the difference of performance between a code level spectrum here, the calculated capacity here, at this point here, coming to this point here, then depending on whether we're just scaling the spectrum down, which would give us this spectrum here, or whether we recognize the spectrum will be different for reduced seismicity and perhaps equal to this, then the peak ground acceleration associated with this spectrum or this spectrum will be different. And we don't take that into account. Now, there are two approaches possible for the displacement-based design of single degree of freedom structures, and I'm only going to discuss the second one, not this one here. They're both in your handout notes. They both have problems with them, but this is perhaps the most consistent approach that should be used for determining the risk of an existing structure itself. So basically, what we do is, first of all, determine a pushover analysis. Hopefully, we can incorporate somehow capacity design effects for this. So we're interested in determining the strength, the maximum displacement capacity, and of course, therefore, we know what the effective stiffness is at the start of this. And we have here the design spectrum, that's the elastic demand spectrum that we would hope that we could attain. The steps are first to determine the force displacement capacity response, so that's the stiffness. We calculate the effective period, we calculate the appropriate level of ductility, and hence the damping associated with that. We determine the spectral reduction factor and the equivalent elastic response from that. We invert the process. The equivalent elastic displacement demand is found from the elastic demand displacement up here, and then the displacement ductility capacity ratio is determined, and hence the seismic risk. So we can actually, with displacement-based approaches, use something or other which is more consistent than will occur elsewhere. We need to include P-delta effects, and in this case, we reduce the base shear capacity by the amount that we talked about when we talked about P-delta effects this morning. So the reduction in the base shear capacity is just equal to this coefficient C times P-delta divided by H, and giving us a reduction in the effective stiffness and hence in the response. There's an example given, which I won't go through, of a simple bridge pier working out based on a very assumed and rough relationship between the capacity demand ratio for displacement and a value for the probability of exceedance. And I won't go through this at this stage, just to show some of the data associated with the flexural response, shown here again, and the shear strength. Shear is not a problem in this particular case, but the ductility demand is. Looking at multi-story buildings, multi-degree of freedom systems, there's more problems associated with this, and the main problem is determining the inelastic displacement profile. So we don't have the luxury of knowing that we're doing a design, and if we do the design properly, the displacement shape is going to be very close to the values that we've got from well-designed structures in the past. Here, we could be varying from having a beam sway mechanism or to a column sway mechanism, and the displaced shape will be very different. In this case, then, some of the things that we need to look at are limit state curvatures. And one of the problems here is, again, we can't just say, well, we can determine a limit state strain and therefore determine what the corresponding limit state curvature is, because now we typically are going to find that buckling of reinforcement and spalling of concrete may be influenced by the spacing of transverse reinforcement in a plastic hinge region. So we've tried to make some estimates. They're not particularly scientific, but they're based on our experience as researchers and engineers as to the influence of the spacing of the transverse reinforcement on the available damage control curvature. And basically what we're saying is that if the spacing corresponds to what is recommended in the book, then basically we have a curvature which can be just calculated in the normal fashion, but will be at least 12 times the yield curvature. If the spacing is 16 times the longitudinal bar diameter, then we have a curvature which is going to be no larger than the serviceability curvature. Once we get past that, we're likely to get crushing of the concrete and buckling of the flexural reinforcement. And so we just provide a linear relationship between those two, which may be reasonable and may not be, but it's at least a reasonable estimate for using as an assessment tool. So in this region, we can just write an expression of this nature to determine what the limit state curvature would be for the damage control limit state. The second step then would be to calculate the plastic rotation capacity of the plastic hinges of the structure. And the third step then to check what we call a sway potential index. And this is again something that's a little bit difficult, but we want to see whether the structure is likely to form a beam sway mechanism or a column sway mechanism. And the way in which we do that is we take each particular beam across a frame or across the entire building, and we sum the positive and negative moments of the beams on either side of each joint and compare that with the sum of the column moments above and below each joint. You know that we want to have the moment capacities of the columns exceeding that of the beams, but we don't do this on an individual column basis. We do it on a complete beam basis from one side of the building to the other side. And depending on what value we get for the sway index, we decide whether we believe we've got a beam sway mechanism or a column sway mechanism. So basically we're saying here that if this index is less than 0.85, then we're pretty confident that we'll get a beam sway mechanism. If it's greater than 1, when we believe that a column sway mechanism is expected. In fact, of course, if it's equal to 1, there's perhaps equal probability of each occurring, but we must be conservative and assume that a column sway mechanism occurs. And between these two cases, the sway mechanism will depend on the actual material strengths, and it may be difficult for us to estimate in this fashion itself. And maybe something more sophisticated should be done. Generally, it's okay to use gravity load and axial load for determining the column flexural strength for this type of analysis. And the reason for saying that is it's rather important because you won't know what the column axial loads will be until you know what the seismic resistance is. But the lateral forces are going to increase the flexural capacity of one column and decrease it of another one in pretty much the same fashion. So it's not likely to change the sum of the column moment capacities, though it will change the individual values. So then we determine the limit state deflected shape. If it's a beam sway, we have the shape as for a new design. If it's a column sway, depending on where we think that the hinges are likely to form, we will get different column sway mechanisms. But on the basis of those, we can calculate the capacity. Beam sway as for a new bridge, new building, and we can calculate the overturning moment capacity from the sum of the column moments and the beam shears. And on the basis of that, we can calculate the base shear capacity as the overturning moment divided by the effective height. And similarly, we can calculate, if we have a column sway mechanism, a similar idea of what the base shear is. The step 6 is to determine the single degree of freedom parameters, the equivalent displacement, the effective height, mass, height, ductility, equivalent viscous damping, and then the assessment continues as for a single degree of freedom structure. We note that column shear failure must be investigated, and column and joint shear failures must also be investigated. And then there's an example shown in your handout, which again I won't bother to go through, but it's a 6-story building with some moderately reasonable detailing, but the spacing of the transverse reinforcement is rather wide, and we come up with something or other where the capacity is significantly different from the required capacity.